I'd like now to talk about some modes of nuclear decay. First of all, let's define the word isotopes. Isotopes have the same number of protons but different numbers of neutrons. So an example of that would be U-238 and U-238. They're both uranium, but they both have different numbers of neutrons. This has three more neutrons than this one does. And the 235 and the 238 represent atomic masses. Let's talk about some important nuclear particles and look at the way that we express isotopes. Alright, so here's the way that we're going to look at this. We've got the X, that's usually the element symbol. The Z is the number of protons, or the atomic number, and Y is the mass number, which is the number of protons plus the number of neutrons. So if you got something like U-238, you don't really even need to put the 92 here, because if you look at the periodic chart, you'll see that you can always pick up what the atomic number of uranium is just by looking at that. So U is 92, and it's redundant almost to include the 92 here. So just U-238 is pretty much all you really need to put. So if you wanted to figure out the number of protons and neutrons, the number of protons would be the atomic number, which would be 92. The number of neutrons would be 238 minus 92, which is 146. And this is an example of one of those heavier elements where the number of neutrons far outweighs the number of protons, and we'll see examples of those and why that might be in a little bit. But let's look at some elementary particles, or some important radioactive particles, or particles of radioactive decay. And you've got the proton, which is 1H1, which has an atomic number of 1, and of course that makes it hydrogen, so it has a mass of 1 because it's just one proton. Now neutrons have a mass of 1, but they have no charge associated with them, so it's 0. The atomic number is 0, and we give it the symbol N. Now electrons have a -1 charge. It's exactly the same charge as the proton except negative, so we get a -1 on the atomic number. And electrons don't really weigh anything, so we put 0 for the mass up there. A positron is the antiparticle of the electron, and they do exist, and we'll see examples of positron emissions in a little while. And what we're looking at is a charge of 1, which is opposite to the electron, but still a mass of 0, so that's a positron there. The other one that's important is the alpha particle, which is essentially just a helium nucleus, has 2 protons and 2 neutrons, so it has a total mass of 4, and has a symbol 2He4, or if you like, just 4He would be fine as well. All right, let's take a look again at this PowerPoint slide. Now what I want to point out is that you've got this line here which represents a 1-to-1 proton to neutron ratio, and you'll notice that down in the smaller elements that's pretty much what you're going to see. You're going to see elements that have pretty much equal numbers of protons and neutrons. Alright, let's take a look at a small, like one of those, let's say carbon-12. Carbon-12 has 6 protons. It weighs 12, so it's going to have 6 neutrons as well. That's 12 minus 6. So it works pretty well for the smaller ones. But as we get up around here, you've got the uranium. We already looked at that one. Uranium-238 was 92 protons and 146 neutrons. So you can see that clearly the neutrons are beginning to outnumber the protons pretty severely by that point. And we see that trend as we go across the periodic chart, and we increase the number of protons. So when we get to 90, you can see we're far outnumbering neutrons with protons by that point. Now these blue dots here, these blue dots represent stable isotopes. These are isotopes that do not undergo radioactive decay. But if you look at the green area represents isotopes that will undergo radioactive decay. And depending upon the relative positioning of those relative to this blue line, we can actually figure out what kind of radioactive decay they might undergo. So above the line, above this blue line, you've got things that have too many neutrons. And below the line, you've got things that have too many protons. So if something's got too many neutrons, what's it going to do? It's going to want to convert those neutrons into protons. And likewise, if something has too many protons, it's going to want to convert those protons into neutrons. Anything to get closer to these blue dots and even become those blue dots. And that's what the whole aim of radioactive decay is all about. Alright, so let's look at the kinds of things we can say about that. Alright, what about above the band? Above the band we had too many neutrons. So those neutrons are going to want to turn into protons. If they turn into protons, they'll get closer to that those nice blue dots. So how can a neutron become a proton? Well, a neutron can become a proton if it emits an electron. So the neutron stays in the nucleus, the proton stays in the nucleus as well, but the electron gets emitted. This is called a beta particle, or a beta minus more specifically, because we want to be talking about electrons being emitted. Now I want you to notice the actual reaction going on here. You've got a mass of 1 for the neutron, and over here the total mass is 1 plus 0, which is 1. And if you look at the charges, it's 1 minus 1, which is 0. So even these particular nuclear reactions will also balance just like chemical ones do. So that's a pretty typical way that things above the band will, above the blue dots, this is what they'll do. They'll tend to emit electrons and turn neutrons into protons. Below the band, those are the things that have too many protons. So what can something do to get rid of protons? Well, there's two things they usually do. The first thing is they can emit a positron. And if you look at the nuclear reaction, the proton turns into a neutron plus a positron. If you look at the way it all adds up, you've got 1 plus 0 equals 1, and 0 plus 1 equals 1. So that works out. So this is a positive electron that gets emitted. And of course, a neutron stays in the nucleus. The other way that this can happen is that a proton can actually absorb an electron from the very first row. Back in the old days, the very first row of electrons used to be called the K row. So what we're talking about here is you've got your nucleus down here, and then you've got your first row of electrons, your second row of electrons. And what I'm talking about is one of these, and it gets absorbed into the nucleus. And this is called K-electron capture. And you'll notice the electron is on the reactant side. That means it's being absorbed, not emitted. And these guys, since they're on the product side, these are being emitted. So that's the big difference of what's going on there. But in both of these instances, the protons are turning into neutrons, and that brings them closer to those nice blue dots, the nice stable blue dots on that graph. Alright, so let's take a look at the graph again. There's your summary. Neutron-rich nuclei will undergo beta decay, and proton-rich nuclei will undergo positron decay or electron capture.